This is an answer to your question that you put out, Jay. This is worth looking over because quite a few students ask about resonance and how it affects bond length. That's why I made this video, to help everybody. Here we've got the question. It's nitric acid's Lewis dot molecular structure is shown here. It's the typical oxoacid where you have a hydrogen attached to the oxygen. You're not going to have the hydrogen attached to the central atom. This is the hydrogen that gets donated as a proton, and nitric acid is a strong acid. It 100% ionizes because it reacts with water. You can buy it, science catalogs and such. In this case, Flynn, which sells a lot to schools, sells about 16 molar nitric acid. You can say you put it in a special container so that it doesn't break, because this is nasty stuff. 70% in terms of by weight. You can get it slightly higher concentrations, 18 molar, but then it's fuming and you don't want to deal with that. Now here are the prices. A 5-liter container is about $50, but you'll probably have to pay at least $20 for shipping, because this can't be put on planes. It's got to be land shipped with special warnings and hazmat stuff. In fact, nitric acid has been responsible for some nasty accidents in terms of shipping. So there's your nitric acid, and this is a new bottle. Typically, they'll put a red cap on it to tell you it's nitric. It's strong acid, but it also has the nitrate, which is quite dangerous. Hydrochloric will end up having a blue cap, sulfuric will have a yellow cap, but typically nitric acid is so concentrated and so nasty that this red cap, after a year or so, will have disintegrated. So let's go back to the problem right now, though. Here's the question about resonance structures and the shape, and typically an AP question might even ask about the hybridization. And as you can see, we've got our nitrogen as our central atom, and everybody here has their octets except for hydrogen, which only needs 2 electrons. That's what those lines stand for. In terms of formal structures, we've got our hydrogen taken care of. We use 1 electron for each one of these shared pairs. So I look at this oxygen, I see 1 electron, 2, 3, 4, 5, 6. It has, because again, with a shared pair, it controls one of the electrons. We would say that because oxygen typically has 6 valence electrons, there is a formal charge of 0 on this. And here, 1, 2, 3, 4, 5, 6. Each one of these bonds contributes 1 electron to the oxygen. Now, this oxygen, though, has 1 electron for the bond, 2, 3, 4, 5, 6, 7. It has 1 more electron than it normally does. This oxygen has a formal charge of -1. Now, a molecule, in terms of formal charges, have their formal charges add up to the charge of the molecule or ion. In this case, we have a charge of 0, so we know this nitrogen must be a +1 for a formal charge, and you can check that if you want to do it. Make sure you've got everything done right, and you can see we have nitrogen, 1, 2, 3, 4 electrons around it, and normally nitrogen has 5 electrons. That's its regular Lewis dot structure, so it does indeed have a charge of +1. When you have formal charges, you expect the negative charge to be on the atom that has the highest electronegativity, and that's oxygen. So this is good. I mean, nitrogen has a lower electronegativity. It wouldn't control the electrons as much as oxygen with the higher electronegativity. In terms of its shape, we have 1, 2, 3 sigma bonds around our central atom nitrogen. And if you've got 3 sigma bonds, let me go back here, my shape table, we've got 3 domains, 3 sigma bonds. That would be trigonal planar, 1, 2, 3, because they'd arrange themselves out as far as they possibly could from one another. And this would be classified as an sp2 hybrid, a s which has one of the hybrid orbitals and 2 over here for the p for the other hybrid orbitals. So we've got 3 orbitals in this bonding. So I'll go back to our nitric and our oxygen hydrogen. So we'd expect 120 degrees as our angles between the oxygen, nitrogen, oxygen. And of course our oxygen here would end up having a tetrahedral structure with 109 here on its nitrogen. But when we draw this molecule, it's possible to put that double bond in another location. Now, we didn't have to put that double bond here to the left. We could have put it on the bottom, and that's what was done in this case. And it's just as valid of a structure. We still have a +1 for our formal charge for nitrogen and a negative 1 for the formal charge of oxygen. So we could have drawn it just as well this way. And actually, this double bond is delocalized because either spot is great for it. And on the atomic level, this doesn't separate as a separate bond. It averages itself between these two locations. So we have two good structures that we would end up referring to as being resonance structures, two possible places for that double bond to be placed. But if you're sharp, you say, well, wait a second, why not put that double bond here around this oxygen and have three resonance structures? Well, the thing that's wrong about this is that this oxygen isn't the same as these two. It's got a hydrogen attached to it. And that's going to give it a different electron pull and a different arrangement. And if you look at the formal charge now, we have 1, 2, 3, 4, 5. This oxygen, if the double bond is placed there to make a pi bond, is going to have a formal charge of +1. We still have our -1 here, but now we've got a -1 here, and the nitrogen has a +1. This is just a wretched structure in terms of formal charge, so this double bond's not going to be there. The basic rule for resonance structures, if you can place this double bond on an identical atom, like this double bond doesn't know the difference between these two oxygen atoms. They're identical. So it would have these two resonance structures. And this double bond then would be averaged, and as a double bond, it's a little shorter than a single bond. So we'd expect these two oxygens to have a relatively short, identical bond length, and then a longer one here for the single bond. Okay, that's our nitric acid, but once that proton is donated, we've changed the molecule into the nitrate polyatomic ion with a charge of -1, and you'll find that in this structure, we end up having where everything adds up to a -1. You could put the double bond in this location. You could put the double bond on the right and still have the same identical and very good formal charges. You could put it on this new location because this oxygen to the right no longer has a hydrogen attached to it. So in effect, this double bond has three possible places it could be, and it's there in all three places at the same time. So this nitrate ion, different than our nitric acid molecule, will have three possible locations for this double bond. This double bond, therefore, will be averaged around all three bonds and have the same length. This is now the conjugate base of a strong acid, and this conjugate base is not going to pick up a proton. You have nitrate ions floating around. They're not going to pick up an H+ because this is a strong acid. The Kb, this is a super, super weak base. It's stable as it is, and that's our last answer. So there is our resonance. I hope that clears things up, and I'm going to post it. Thank you, Jay.